Now that we know how to differentiate sine and cosine, we can study simple harmonic motion. And let's start our discussion next with example 5. In fact, let me first read what example 5 exactly says. A body hanging from a spring is stretched 5 units beyond its rest position and released at time instant t equal to 0 to bob up and down. So that's how you have simple harmonic motion. Its position at any later time is given by this equation s equals 5 cos t. You already know that here t represents time and s represents distance. Although cosine and sine functions did not appear when we previously considered examples of rectilinear motion, but at least we know that t is time and s is position. So then we have to find the velocity and acceleration of the body at any time t. So you have this accompanying figure to describe the situation. Now in this figure, the first thing you notice is, of course, you have the system consisting of the body and the spring, but you need one more thing. In order to measure the position of the body at any time, you are going to need a position axis. So this is that position axis S, on which numbers increase downward. Now initially when the system was like this, when you did not pull the body down, when you did not stretch the spring, you of course want to put 0 here on the position axis, which coincides with that rest position of the system. And then what you did, you pulled it by 5 units. So the spring gets stretched, and if you then release the body, the stretched spring will try to assume its original position back, and in doing so it will pull the body up. So after some time that state is regained, but of course due to inertia the system does not just abruptly stop there. The body overshoots this rest position and goes above that. And in that part of the journey, the spring gets compressed. Okay, and the body finally assumes some maximum height, which of course will be -5 here. But in this state also the spring is not happy, so it will try to push the body down, because this is what the spring wants. That's how it wants to be. So again the body, due to inertia, overshoots the mark and this motion continues. So that is captured in this equation. Because cos t is a function which takes the same values again and again after regular intervals of time, that is why you see this appearing in the description of such a motion. Alright. So let us now calculate the velocity and acceleration. And then from those things, we will be able to say some things about this motion. So obviously the solution will be this. It's nothing surprising. You already have the position given, s equals 5 cos t. Now to calculate the velocity, we have to differentiate this with respect to time. So when you do that and 5 comes outside of the differentiation process by the constant multiple rule, so you then have the derivative of cos t, which is minus sine t. So that way you get the velocity to be -5 sine t. And then when you go for acceleration, that is the derivative of velocity with respect to time. So now you differentiate this with respect to t. So -5 goes outside, and the derivative of sine t is cos t. So that way you get -5 cos t. Now using these things, we are going to say something about this motion. So just from the position function itself, we can say this. As time passes, the body moves up and down between these two marks, s equal to -5. You recall the figure, s equal to -5 and s equal to 5 on the s axis. the amplitude of the motion is 5. How are we able to say that the body will move between minus 5 and 5? That is because the position function s is 5 cos t. Now, no matter what t is, t can be any time after 0, 100, 1000, anything. Cos t has maximum value 1 and minimum value minus 1, and as such s can have maximum value 5 and minimum, I should say like this, maximum value 5 and minimum value minus 5. That is why the position of the body is forever trapped between minus 5 and 5 because of this equation. Okay, so actually we are telling all these things just from this equation, not these things. There is one more thing. The amplitude of the motion is 5. The amplitude is how far the body can move from its mean position. Mean position is that 0 mark. So it can move maximum 5 units on either side of the mean position. There is something else. The period of the motion is 2 pi, which is the period of the function cos t. The period is when the body is in one position of motion and the next instant when exactly that state is assumed, state of motion is assumed, the duration between these two consecutive exact same states of motion is the period. Now, if you want to see that in that figure, so let me show you again exactly why the period is 2 pi. Not simply just mathematically saying that because the period of cos t is 2 pi, so that is also the period of the body. Let us also see physically why that is the case. With this figure, not as nice as the last one, but you will understand what I am trying to say. So this is what we previously had. So what is the period of the body? So in the stretched state of the spring was here, okay, the body was here and the spring was like this, and that's when the motion started, and that is also the instant t equal to 0, and that in fact is reflected in this equation. If you substitute t equal to 0 here, cos 0 is 1, so s is equal to 5. So yes, s is 5. This is where the body is lying on this s axis. But then as t increases, cos t also changes and the body goes up. Alright. So we have to see how long the body takes to come back to this exact state of motion. This will happen again and again. We have to see the time that it happens again for the first time. So the body goes up. Let us put some values of t and see some special known values of t, for which cos t is known, and see where the body lands up. So after t equal to 0, what will happen if you put t equal to pi divided by 2? Cos pi over 2 is 0, so s will be 0. So at t equal to pi over 2, at that instant of time, the body assumes its mean position, or rather the system assumes its mean position. What happens if you take higher values of t, say t equal to pi? So we put t equal to 0 and then we put t equal to pi over 2. Now if we put t equal to pi, cos pi is minus 1. So s becomes minus 5. So when t is pi, this is the position assumed by the body. Okay. But then it will again come back down. What happens if we take a higher value than pi, say 3 pi divided by 2? 3 pi over 2 is an odd multiple of pi, so their cosine will again become 0, just like pi over 2. So then while coming down, at that instant t equal to 3 pi over 2, the body assumes the mean position. Note one thing carefully, that although that was also the mean position the first time the body was here, and now while coming back this is also mean position, these are not the same states of motion. That first mean position was attained when the body was going up, and the second time the mean position was attained when the body was coming down. Okay, so these are different states of motion. But anyway, so it comes down, and then finally at t equal to 2 pi, at that value cos t again becomes 1, just like 0. So you get back s equal to 5 position. So it takes time 2 pi to regain that same state of motion, or in physical language, one complete revolution happens during that time interval. So that is why that is the period. I say revolution, but one complete, what is it called? Oscillation, yes. Oscillation happens during the time interval of length 2 pi. That is why that's the period of this body. And is it not magical that that same thing mathematically is also the period of cos t? They should match, we feel that, but actually that's the case. Next, let us see what we can say about velocity and acceleration from these things that we found. We come to the velocity of the body. So the velocity is minus 5 sine t. We have already calculated this. So I instead used this part to bring back that diagram. The function sine t attains its greatest magnitude when cos t is equal to 0. Why? Well, you can recall this basic relation. Sine square t plus cos square t equals 1. This is something so familiar to us that we did not even bother thinking about this. But you will notice from this that, of course, when t changes, sin t and cos t both change, but the sum of their squares is 1. Now, what this equation tells us in particular is that as cos t increases in magnitude, because note that there is a square, so whether cos t actually is positive or negative, that here at least does not matter. As cos t increases in magnitude means as cos square t increases, obviously sin square t has to decrease because the sum is constant. Similarly, when cos square t decreases, sin square t increases. So to maintain this balance, the function sin t attains its greatest magnitude when cos t is equal to 0, and when cos t is 0, sin square t is 1. So sin t is either plus 1 or minus 1. We already know that sin t attains the maximum value plus 1 and minimum value minus 1. But when looked at from this point of view, we see that simultaneously that is the case when cos t is 0. Okay. So when cos t is 0. Now you recall what the original position function was, s equals 5 cos t, and for which values of t is cos t 0 odd multiples of pi over 2, and the position on the s-axis that corresponds to cos t being 0 is this, because that's when s is also 0, and that is precisely when sin t has greatest magnitude. So if you take the absolute value of velocity, you get speed. So speed is maximum here, which matches with our experience with this type of motions also. As the stretched spring pulls the body up, initially the speed is not that much, but this is the instant when the body has the greatest speed. But then as it goes above this mark, its speed gradually again decreases, becomes 0, and then the velocity gets reversed and then it starts to increase in magnitude. The direction has changed, but again the velocity has greatest magnitude here. So this is the place where velocity has greatest magnitude, that means speed is the greatest, which is what we expect from our experience, but now the equations have shown that yes, that is really the case. The body's speed is 0 when sin t is 0 obviously, but sin t is 0 precisely when cos t has maximum magnitude, that is either cos t is plus 1 or cos t is minus 1. When cos t is plus 1, the position that the body assumes is 5, and when cos t is minus 1, it is minus 5. So these are the two instants when speed is 0. Yes, that is true. The motion starts here, the body goes up and momentarily stops. So there the speed is 0. Again it comes down and it stops here. Again the speed is 0. So that thing has also been revealed by these equations. Next, let us see what we can say about acceleration. Next we have acceleration. Acceleration is minus 5 cos t, and acceleration is 0 only at the rest position s equal to 0, because s is 5 cos t, s is 0 if and only if cos t is 0. And actually, how can we make sense of this physically? Well, that is there in the next line. When the body is anywhere else other than this position, the spring is either pulling it. If the body is below this position, the spring is pulling it or pushing it. When the body goes above this mean position, the spring is pushing it. So there is a force on the body anywhere during this motion except at this point. So if there is no force, obviously there is no acceleration due to Newton's second law. So that is why. And the acceleration is greatest in magnitude when cos t is plus or minus 1, because that is the maximum numerical value that a can have regardless of the sign, and that corresponds to these positions. When cos t is 1, s is 5. So then the acceleration has maximum magnitude and the magnitude is 5. And when cos t is minus 1, then s is minus 5. So there at that instant also the acceleration has the greatest magnitude 5. So this means that as the body is going against the will of the spring to stay in that position, at these extremes that becomes maximum. So that is why force applied on the body by the spring, whether it is pulling or pushing, that is maximum. So acceleration is also maximum in magnitude. Now before we leave this example entirely, let me draw your attention to one thing. You go back and see the position function of the body, s equals 5 cos t. Does that function tell you that the system is eventually going to come to rest? No. S equals 5 cos t, and as t changes, s keeps on changing. There is nothing in that equation that tells us that eventually we are going to assume this mean position. However, that does not match with what we see in real life. In real life, if you pull a spring like this, then of course the body goes up and this up and down motion happens, but the amplitude gradually decreases because energy is lost to the outside environment. When you are pulling the spring, you are applying some, you are doing some work against the will of the spring to get stretched. So that work is stored in the system in the form of potential energy at first, and then when you release it, it gets turned into kinetic energy. Then when it again comes to rest here momentarily, that kinetic energy gets turned into potential energy, then back to kinetic energy. So this transition keeps on happening But at the same time, due to air friction and many other things, energy is gradually lost from the system, and that is why the amplitude decreases and the body eventually comes to rest. But that means that what we are studying here is not a real situation, it's an ideal situation. If you take into account loss of energy, then the equation won't be this simple, S equals 5 cos t. There will be something in the equation that takes into account that expresses that loss. So after some finite time, there won't be any, I mean, of course there will be energy, but not that type of energy. Whatever energy you gave in the system, that will be lost to the outside environment. After this, there is one more notion. So you know what position means, what velocity means, what acceleration means. There is something else also called jerk. So that's the next thing we are going to see. So next we have jerk. This word actually should not be interpreted in this context as a swear word. Okay? It's a technical word. Jerk is the derivative of acceleration with respect to time. So if we take one more step in our subsequent differentiation of these things, subsequent differentiation of position. First we differentiated position with respect to time, we got velocity. Then once more we differentiated, we got acceleration. Now if we do it once more, we are going to get jerk. So that means it's the rate of change of acceleration of a body with respect to time. It's not necessary that the acceleration of a body should stay constant during its motion, no matter what type of motion it's undergoing. That of course is not the case. So it can also change, and it does change. So we can calculate the rate at which it changes, and that rate is jerk, J. So it's dA over dt, and that is the third derivative of position S with respect to time, if S is the position at time t of some body. Now this jerk is actually really a jerk. This is responsible for motion sickness that we all experience when we are traveling, say by car. So what happens is that it has been revealed in experiments also that changes in acceleration is what causes motion sickness. Now it can be a change in the magnitude of acceleration or its direction. So if you are driving by car, the car slightly changes, I won't say position, but the direction of motion. Say you want to avoid a bump, or you want to avoid some pothole, something like that. So you have to swerve it. So you have to do constant adjustment with your steering wheel, and in doing so, acceleration changes all the time, and that is what makes us sick. Now if you are focusing on the road, say you see the road in front of you through the windshield, and you see what is there in front of you, that oh, there is a speed breaker. So that means now the motion is going to be like this. So your brain gets prepared for that. That is why drivers don't get motion sickness as much as passengers get. And that too, when someone is, say, sitting in car and reading something, then quickly that person feels sick because of that thing. If you are not looking outside, you do get sick because you don't know what is going to happen. So these acceleration changes affect you more. Now finally, let us calculate the jerk in two situations, in two types of motion. So this is example 6. Part A of course considers a motion with, say, a constant acceleration like free fall. The jerk of the constant acceleration due to gravity is of course 0, because jerk is the derivative of acceleration with respect to time. So if the acceleration is constant, so there will be it will be 0. But what is the jerk of the simple SHM means simple harmonic motion in example 5 that we saw just now? That is dA dt. Now a there was minus 5 cos t. So minus 5 goes outside by the constant multiple rule of differentiation, and if you differentiate cos t you get minus sin t. So minus 5 times minus sin t is 5 sin t. So this is the jerk of that simple harmonic motion, and it has the greatest magnitude of course when sin t is either plus 1 or minus 1, and correspondingly when cos t is 0. And by now we know very well what position this corresponds to, that is the mean position. So initially suddenly you may think that because the motion is like this, at the extremes of the motion you are going to get a jerk because it's coming back. No, actually that's not how it's happening. Do not forget that as the object or as the body goes up, its velocity actually decreases, and it very nicely comes to rest, and then again it picks up speed during its downward motion, and the same thing happens during the other half also. It goes down, but as it does so, its speed decreases, and then again slowly it picks up speed. So there is no jerk, but the jerk happens at the mean position, because there suddenly push changes into pull. That is why there you have maximum jerk. That is when the acceleration changes direction and sign. As the body was coming down, it was push, so the force was in this direction, and the moment it overshoots that mean position, that push suddenly turns into pull. So the force changes direction, acceleration also changes direction, it has the same direction as the force. So that's where you experience a jerk. So that will be all for today. In the next calculus video, we are going to see how to differentiate the other 4 trigonometric functions. And tomorrow we do not have any upload. Day after tomorrow we have our usual analysis where we have more problems to solve. So let me just end the video here and see you with analysis. Until then, this is me, Lucifer from a mathematical room. Have a nice day.